Good morning, everyone. Thanks for being back. I hope you enjoyed yesterday's night. I'm very pleased and honored to welcome Malcom Sambridge for this third keynote presentation of IAMG 2022. Malcom graduated from the University of Cambridge and then he got a PhD from the Australian National University, where he's currently a professor in geophysics, computational geophysics, and mathematical geophysics. And it is his first IAMG conference, and we are really pleased to have him. He has made very important contribution to inverse problem theory, methods and algorithms, including, among others, the neighborhood algorithm. He also made very interesting work on Voronoi diagrams and their use for spatial interpolation and estimating physical quantities in the subsurface. And today he's going to talk about a big topic in geophysical inverse theory, which is optimal transport and how to use it to get good objective functions. But I'm sure he will tell you that in much better than I do. Welcome, Malcom.
So thank you for that, Guillaume, and thank you for the organisers, and I'm very pleased to be here for the invitation. And also to this session, some great talks lined up in inverse problems. So yeah, I wanted to talk about optimal transport and geophysical inversion. It's a very broad title, so actually I can talk about anything underneath that umbrella. That was deliberate. And it's really a summary, in part, of what's in this paper that was published very recently in GJI with the same title, with co-authors Andy Jackson and Andrew Valentine. They're not responsible for anything you object to today. Okay, so if you're interested in inverse problems, you inevitably have to have some measure of fit to data. Seismologists on the left-hand side here are often dealing with time series, of course, and they have to measure how well predictions match observations. But there are many, many examples, of course, and we've seen some in the conference today. On the right-hand side of tsunami, data sets are large and complex, but to drive any fitting process, or even for other purposes, we need to know how far away we are, what the quality of fit to our data is. And that's the topic that got me interested in optimal transport. So I'd like to use this slide to talk about two common questions we use in data. So on the left-hand side, you'll see a misfit surface, a multimodal misfit surface where we're trying to presumably find the minimum, which is in the well here, the red well. And an approach to inverse problems is to fit data, to do optimization. So this is our fit to our data as a function of two parameters, and we're driving that towards some sort of good solution. And then we might do some sort of error analysis about that solution. On the right-hand side is probabilistic sampling, which is another popular approach, which combines essentially finding models of good fit with uncertainty, a probabilistic stance to inverse problems. And both depend upon measures, of course, of how well you fit your data and how far away you are from fitting data. And so optimal transport has applications in both of these areas, and I'm going to talk about a bit of both of them, starting with the one on the left and ending, if I don't go over time, with the one on the right. Okay, so I like to start with audience participation. What's the distance between A and B? Well, I've done this to my students, and of course they will say, it's along the straight line between A and B. And that's okay if you want to take a straight line. We actually saw Southeast Australia on Philippe's slide yesterday, and there's another example of Southeast Australia. If those 2 points that we want to move between, we want to transform ourselves from A to B, that's not the path I take when I go to my favourite beach in Southeast Australia, which is Lilly-Pilly. That's the path we take. Yeah? So the distance between A and B, for me, to drive there, is the blue path. Yeah? As the crow flies, it will be the black line, of course. So the path and the distance we take between A and B depends upon the path, and an optimal path here is the straight line A and B. So actually, when we think of the distance, Euclidean distance, it is the result of an optimization. It's the optimal path of all paths that give us a minimum distance. Yeah. So this notion of a path between two endpoints and the distance between them are uniquely linked. Yeah. This brings us to 1781 and optimal transport. So the lovely story that starts off optimal transport is Napoleon II asking Gaspard Monge how to move his sandcastles around. If you imagine that the orange on the left here is some pile of sand, of any arbitrary shape, and on the right is a hole in the ground, or two holes in this case, of a different shape. The only constraint being that the complete volume of sand on the left is equal to the space on the right in blue. Yeah? And the question says then, how do I move the sand with minimal work? Because I'm lazy, I want to have minimal work. How do I move this sand? Which parcel of sand goes into which part of which hole? And that's essentially the problem of optimal transport, physical realization of it. The mathematics comes down to the expression below. If you look at that integral, WP, the integral is, if you look at it, it is x, the position where the sand starts, the distance to t of x, which is where it ends. So it starts at x, goes to t of x, distance, I put a p norm in there, say p is 2, the Euclidean distance squared, so where I take a little parcel of sand, I move it, I square the distance, I multiply it by fx dx, which is just the density of the sand on the left. So fx times dx is actually the volume of sand, the parcel of sand, and it's that parcel of sand, the mass of the sand being moved and times by the distance squared. And if I integrate that, I sum over, I'm actually summing the entire work I'm doing. That's proportional to distance squared times mass, which is proportional to energy. So if I take P equals 2, that actually means the amount of work required to move a parcel of sand from x to t of x. And of course, t of x is the thing I don't know. What's the most efficient way of moving the sand? So the modern field of optimal transport dates back to Kantorowicz's seminal work in 1942, of which he eventually won the Nobel Prize for Economics for, and Vigliani's work, 2003-2008 books, where he won the Fields Medal for all on work related to optimal transport, or as it was called then, optimal transportation. So it's got a lot of mass behind it, and it's actually an exploding field. It's a lot of interest has come largely from the recent work by Vigliani across the sciences, and it's creeping out into other fields. And in the geosciences, at least for 10 years, people have been using this idea. So succinctly then, from just a simple mathematical viewpoint, optimal transport would be to take a profile, a density profile, which is blue here, and transform it into the red. And to do that, I use some function t of x, which is where all the parcel of x is moved to. Now this is what we call a transport map. So as the dashed line shows, the little parcel of blue here moves to the place at red here. And it's a one-to-one map. Here's my expression of the work done, and if I minimize WP with respect to the function t, and I'm calling the optimal map t star, then that becomes what we call the Wasserstein distance. It's a distance metric. The condition on t of x is this expression down here, that g of t of x, so that's where the sand goes to, multiplied by essentially the derivative, how much the volume of sand changes as we change the function, is f of x. So this is the constraint. This is a mass conservation constraint, essentially. So together here is essentially optimal transport. And optimal transport problems are not that easy to solve as posed here, because it's nonlinear functional optimization. And I like to do things simply. So I appealed to Kantorovich, who in 1940s worked out a much simpler version of this and showed that it's equivalent to linear programming. So if we think of rather than a plan but a matrix, let's say we discretize the problem, the transport plan on the left. On the right here, we talk about this as a transport plan, which means that in principle, every parcel of sand can move to any other parcel of sand. We're actually solving for every pair of variables, so how much the sand here moves to any part along there. Then we actually solve for a complete matrix, which is simple in a formulation, big in computation eventually. The expression for the Wasserstein distance becomes simply a linear function of pi ij times Cij. Cij is the distance between point I on the source to point J on the target. But that's a linear function. We're searching for pi ij, which is the transport plan now rather than map. Yeah. Under the condition that the sum of this matrix over columns is equal to Fj and the sum over rows is equal to Gj. Now, that means that we've just simply preserved mass. And this is beautiful, simple formulation, and it's a well-studied problem, so we can solve pretty much any problem in optimal transport with this approach. It's just computationally inconvenient at times. So here's an example of optimal transport. I'm going to show you a few pretty pictures showing some examples. On the left-hand side is, this is a calculation I did, is a torus of dots. So this is point masses. You can think of, again, each of those dots being a parcel of sand. I've coloured them in so that you can see where they go. The colouring is completely irrelevant to the problem. There's the same amount of sand or mass at each dot, and it's just the location that matters. So, for example, the green dot here moves somewhere over here. And what we're moving is from a circle or a torus to a, what bird is that? Kookaburra, a kookaburra on the right, a famous Australian bird that has a nice laugh. And what we do here is you can see, the point of this is showing that you can transform the object of the torus into the kookaburra. And it makes sense. This is the optimal map, that things that are close in one become close in the other. But I get mapped, so the blues and the reds and the greens, you can see that they're more or less consistent. This is using solved what we call a sliced Wasserstein algorithm. I won't go into that, but it's a sort of fast, approximate way of trying to solve the same problem. And you can see that there's a coherent mapping. So we get this idea that as you transform one object into another, and it turns out it's really quite general, the objects you can transform, you also get a measure of the distance. So the concept of the distance between the torus on the left and the kookaburra on the right. It naturally falls out, and that's the Wasserstein distance, calculated as I showed previously. Okay, so this is work of Solomon, some great photographs here of how you might transform a cow to a duck to a torus. Yep. The point of this figure is to show that it can be used in more general situations, but also that it forms a metric where the cow and the duck, let's say, what's halfway between a cow and a duck? Well, it's this figure in here. It's the duck cow. What's halfway between the torus and the duck? It's the tor duck. And what's halfway between the torus and the cow? It's the tor cow. Two arbitrary objects, we can describe in a reasonable geometric way what the distance is between them. Cow, duck, and torus. I could put 3 geological models in there. Yeah? I could put 3 landscapes or 3 objects of almost any kind into this and work out what the distance is between them, because it's the work done in transforming one thing to another. And that appealed to me very much, because in inversion we're always talking about how does this, in my case, often time series convert into this time series, or how does this tsunami sea surface profile compare to this profile? It provides a sensible, consistent measure of the distance between them, and also how you transform one to the other. Now, this is an example where it's being used in graphics. how do you take the color map of the dot of the here, this color map being mapped onto this image here creates this one here. The ways you can use these ideas are actually limited only by your imagination. There's all sorts of really quite inventive ways people are using optical transport, which I think is very interesting. So I don't actually know how that's done. Thank you, Jared, for passing that figure on to me. It's from a publication in 2007. So one obvious place you could put this is in mixture modeling. Now, mixture modeling is an example here where we have a sum of Gaussians, we have some sort of observed distribution, and we used to fit it with a sum of Gaussians. This isn't necessarily a particularly difficult problem. It's just an illustration that here's the misfit surface in terms of two means of two of the Gaussians fitting some data by least squares, so it's just simply taking the squared difference of the two curves. This is the optimal transport misfit surface, the Wasserstein distance. It's symmetric about the diagonal, of course, because you can interchange two mean. It doesn't actually matter, so it's only half of the diagonal of this figure that makes any sense. And it's just got a single local minima rather than multiple in a least squares sense. And this is the point I want to explore in the next few slides. Okay, so a nice convenient approximation that we use in our paper is to represent 1D PDFs by a set of point masses, just like the kookaburra. So f of x becomes a sum of amplitudes, f of I, which are arbitrary, and a sum of positions at xif, which are also arbitrary. So that represents the input PDF, or really density function. I say PDF, but really there's no need to say P here. It's a density function. And the final density function, another arbitrary, also represented by a point mass. And if you do that, you actually, some of the results fall out really quite nicely. Okay, f of x here, my notation is the commutative distribution function. F inverse is the inverse commutative distribution function. So in that scenario, we actually get some very nice simple results for 1D problems. This is Viliani's result that showed that in 1D, these problems can be solved exactly for a continuous distribution just by essentially mapping the inverse commutative distribution functions together. The Wasserstein distance here becomes simply just the integral of the difference between the two inverse commutative distribution functions, which are easily calculated for 1D problems. It turns out if you use the point mass and substitute into there, you get a nice little expression which is in our paper. It's not particularly new, but what I want to point out is that the Wasserstein distance becomes essentially just the dot product of two quantities. One is the location, the differences in the location of the point masses, and the other one relates to an ordering of the point masses. So it's one order and one dot product, which is extremely computationally efficient. Yeah? So it's a sort of n log n for an order and an n for a dot product. So it's sort of n squared log n. Yeah? But that's extremely efficient, especially with vector or parallelized machines, for 1D. On the bottom side here, I've done a simple linear program. That's the Kantorovich. The red line is the Kantorovich cost for these problems as I increase the number of dot points. The green blown up here is evaluation of the dot product and the sort. So that's the green, the analytical solution. And there are other methods. Here's the blue line there, which is a finite difference solution of the Monge-Ampere equation, which is very popular in exploration geophysics for these problems. So that's essentially a PDE, solving the same problem via a PDE approach using finite difference. And they're very efficient, but that's simply just 1D. In 1D, we have analytical solutions, so there's no need to do anything really with finite difference, but in higher dimensions, we don't. Okay, so with that in hand, this is really the point I want to get onto. Okay, so how do you transform the two Gaussians into the central Gaussian, the blue to the dashed line? Okay, so I'm going to play you two little animations. The top one is going to be the Euclidean path between the two n members. The Euclidean path is just the weighted average, where I change the weight. Yeah. The Euclidean path between the two Gaussians and the one Gaussian, green to red here, is that the two paths here will just simply change their amplitude. That is the nature of a Gaussian Euclidean norm. So that's the path taken as we go precisely from one n member to the other using essentially least squares, the difference in the squares of the amplitudes. Yeah? And below is the optimal transport path between the two. Yeah? And I never get tired of watching that. And what you see is both start off in the same place, both end up in the same place. They take a different path and therefore have a different measure of distance. But the key point is that whereas in the top case, with the Euclidean norm, all we're doing is using the x-axis here to identify where we compare amplitudes. Now, we just difference the two amplitudes, and one amplitude moves to the beginning and the end point independently for every point. With optimal transport, it works in a higher dimensional space. It works in both amplitude and, in this case, x variable. So it's defining the combination of the two to pass from one to the other. Yeah? It's combining both the lateral position and the amplitude and finding the smoothest, simplest path, and is therefore fundamentally different and a fundamentally different measure of distance. Okay, so going on to seismologists like me are very used to looking at and enjoying time series. Here I have two time series at the top. I'm calling that an observed. They're both synthetic in this case. This is a receiver function, what we call a receiver function, used by seismologists to look at the near surface, or at least one-dimensional structure independent of what's happening further away by the seismic source. And we often want to fit receiver functions. So if I gave that to any student, they say, oh, the easiest way to fit is just to move one to the other. In fact, they're more or less a displacement of each other. Not quite, but the main peak is just displaced. But the Euclidean norm doesn't see that. The Euclidean norm only sees the differences in amplitudes at each point along the time axis. And as such, it will experience a misfit function which is quite complex for this seemingly trivial problem. An example is below, where I've used a double Ricker wavelet, following examples like this by Bjorn Enquist and Flores in 2014. So I've doubled up, I've got a blue Ricker wavelet, a blue double Ricker wavelet, and an orange noisy double Ricker wavelet, and I'm simply going to, as a function of time offset, move one across the other. Yeah? And as you get below, the red dot is where we are in time, and of course what you get is, below is the least squares difference, so it's the sum of the differences between the amplitudes, and of course you see a multi-minimid misfit function, and that's simply because we align, I'll do that again, there we go, the phases come into line like now, we get a local minima, we get a few more here, and as we go up we get to the global minima now, and of course we get local minima later. And so, from an inversion perspective, although this problem is trivial, but just simply from an inversion perspective, the area of optimization that things will converge in the linear iterative method is here. I need to start my waveform within sort of half a cycle for it to converge. Yeah? And in this case, that's simple, but when the wavefront depends upon Earth model parameters, which are hidden over here, or source parameters, knowing where to start may not be trivial. If we have problems where we have very good starting guesses, then there's no need for anything I'm talking about, yeah? But if we don't have good starting guesses, while we're outside of the linear regime, we're in trouble, and we have the classic problem of cycle skipping. Okay, so here's essentially the same figure again for that previous curve. The path in those two waveforms at the top is just as it was with the two Gaussians. It's amplitude-based only, at times indicated by the time axis, whereas in optimal transport here, the path actually changes both amplitude and time. So I've put some snapshots in color here. We can see that as we move from one path to another. And here's the same thing for this is a classic example from Enquist and Flores, but with double Ricker wavelets. The top is what you've just seen, and the bottom is the Wasserstein distance. It's known to be quadratic as a function of time shifts, regardless of the complexity of the medium. So that's sort of inspiring that we can use this quadratic property to extend to more complex problems. Yeah? It doesn't see local minima, it's global. It doesn't matter where I start. If I was trying to optimize this, I would get there with a quadratic optimization immediately. That's because the way we transform between the two objects is different, and therefore the characteristics of the measure of distance are different. So as I said, this has been worked on in sections of the geophysics community for quite a few years now. Here are some of the earlier papers, particularly the work by Bjorn Enquist and his group, and Luda Metivier here. Some very interesting papers going off in all sorts of directions, but applying it to exploration geophysics, full waveform inversion. And these groups are very active and have continued extending these ideas. Yeah. It's broken out into other fields more recently. A paper in 2019, which I think has Thomas Bowden as a student there, as a co-author, and Huang on gravity inversion, seismic receiver functions. And, I mean, there's a talk, of course, here on Friday by Bruno Levy, which I will be very interested in finding out about the latest ideas in optimal transport, so I encourage you to go to that. There's a poster outside by Alex Lipp, who's here, I think, on optimal transport, using it for different types of problem. And I think the challenge here is to find new styles of problem that you can apply this distance function to. And it has some interesting properties. If you look at Alex's poster, you actually see other examples of how it improves over simple least squares measures. Okay. So, and these papers are continuing. The work is sort of, these sorts of things bobble along for 25, 30 years. They get discovered by a new field, and then suddenly creativity pops in and applications appear in all sorts of interesting ways. And I think that's the stage we're at with this now. Having said that, it's not a done deal. Between all these studies, the solution methods for the Wasserstein distance vary, and there are a number of different. It's all a question of fit for purpose, computational cost, whether you need derivatives of the Wasserstein distance, whether it's in 1D, 2D, or higher dimensions. So in here, particular examples in some of these papers are about, in seismic reflection work, is whether you look at one trace on their own or two traces together as an image, etc. So it's really a question of how you pose the problem, how you're going to apply optimal transport. Okay, so in the paper that that myself and the two Andrews have worked on for a number of years, I should say that I first came across optimal transport from Andy Jackson when I visited him in Zurich at ETH. He's the one that gave me the bug on it. You will have noticed, the Keynote spotter there would notice that I'm talking about time series, and time series don't naturally fit into this framework, in fact. A density function is positive. We don't have negative densities. So optimal transport works between essentially positive density functions, whereas a time series is not positive. So there is a question, again, the posing question, which is always the issue, of how you transform a time series to something which is entirely positive. Now, that has differed dramatically over the years by different people. For example, if I have the red and the blue here, which are the beginning and end target waveforms, I could just simply add a constant and make them positive. I could take the absolute value. I could take the positive part of the blue and fit it to the positive part of the red only, and the negative to the blue, the negative to the red inverted. Or there's even an interesting thing called a global strategy where you take the positive of the blue and the negative of the red inverted and take that as one distribution fitted to the positive of the red and the negative of the blue. All of these have certain problems and issues. Issues of preservation of mass, impedance contrast in the application gets lost, artificial discontinuities occur, although you can, so some of these cases where you can measure the distance of the endpoints, but you cannot actually sensibly get a path between them, or it doesn't stay as a waveform or a time series. So this is an open question. And so Metivier and the Grenoble group came up with a very interesting idea, I think, is this idea of graph space OT in the 2018 paper, where they project the whole problem into a different dimension. Rather than considering a 1D waveform, they consider it as a two-dimensional object of point masses along a waveform. And that's very interesting, because then you have to make certain assumptions about how the density, what your distance measure is, but then you map points that are in blue to the points in red. You've got rid of the negativity problem. Yeah? You've turned it into a spatial location problem. And that's what they call graph-based OT, and that work has certainly continued on and is looking very fruitful in the full waveform inversion. So I'm more of a global seismologist, and we're interested in fitting waveforms of surface waves, of body waves, of all sorts of different seismic phenomena or functionals. And typically the problem there is windows are not necessarily aligned. Our phases might be quite considerably separated. So if you use a Euclidean norm, of course, you need common waveforms. Yeah? You can only difference where you see both waveforms. If you actually don't see, if you know you've got noise and they're separated, that doesn't work so well. That creates the type of features we see that I've shown. So the way we've gone about this approach, which is really the contribution in the paper, is to say 3 steps. Let's take our waveform, whatever it is, our time series, and simply rescale the amplitude and the time using this transformation here, and that's simply to allow any so I'm mapping plus and minus infinity in amplitude down to a finite scale here, using an inverse tan transform, and I'm just simply shifting linearly in time. So this is essentially a normalization process to put ourselves on a plane where we can now measure distances. And I think that's reasonable. Most people do things like that one way or another. So we're going to work in this sort of dimensionless plane of a transformation. And of course, there's choices made here. Okay, so once we've done that, step 2 in our approach is to say, let's take the waveform and let's just flow the waveform out across the plane, turn it from a 1D object into a 2D object. And that's done here. I've shown essentially the nearest point, contoured the nearest distance field to the plane, to the waveform. Yeah, I love this one as well. This is showing, essentially the calculation here is identical to seismic wavefront tracking. Yeah? If the time series is a wavefront and you propagate it out, that's the wave field you would get. But this is a simple calculation. Fast marching can be used to solve it, or other methods. So we're now converted the 1D object into a fingerprint, a 2D object. And then I'm simply going to put those things to the power of e to the minus d. D is that field over lambda. Lambda is going to be a scaling factor of choice again. And I get a 2D object like this. Okay? So I've solved the problem of positivity by turning things into a surface. Very similar concept to the Grenoble's group, in fact. So I now have 2 surfaces, and I'd like to compare them, 2 time series that have been turned into surfaces, where the ridge of this function here is the original time series. Now, I could do this via 2-dimensional optimal transport, but time series have a very particular property in that they are unique in time. So by definition, you've got 1 amplitude per time. So what I've simply done here is take the marginals of this distribution, I integrate it down to the amplitude axis, here, and the time axis here, to create what we're calling a time amplitude density function, and on the vertical bit, an amplitude time density function. So 2 1D functions rather than a 2D function. And what I'm going to do then is suggest that we should use these density functions that are all by definition positive and normalized, so I can compare the amplitude density function between 2 waveforms or the time density function. Now, it is not the case that the time function only has time information. It actually has amplitude. Amplitude information here is encoded in the time axis, and time information is encoded in the amplitude axis. The reason that this is appealing to us is that it takes advantage of 1D analytical, fast, exact solvers for optimal transport. Time windows can be separated. The computational cost scales with n rather than n squared if you've discretized the 2D medium, and that can matter because algorithms then essentially square that, so it could be n to the 4th if you use the 2D medium, but it's only n squared with 2 1D medium, 1D lines. And most importantly, from my perspective, you can calculate derivatives of this thing analytically. So the derivatives of the ultimate Wasserstein distance, which might be the Wasserstein distance between the amplitude density functions and the time density functions, with respect to the amplitude of the original wavefront, can be calculated analytically exactly. And that's very useful if you want to use this in a fitting process. But all the details are in the paper. So the question I usually get is, well, okay, by going from a 2D field, which actually I've made up from a 1D field, and looking at the two marginals, you've lost information. And that's true, you have lost information, but the nature of the information we've lost doesn't appear to be that much. For example, if I displace this waveform in the amplitude, then the amplitude density function shifts, the time density function doesn't change at all. Yeah? So I cannot detect those changes. But in my game, constant shifts in amplitude don't occur. In fact, we have no zero frequency measured. So the average is always zero. So that's irrelevant to us. And in here, similarly, if I shift it in time, which we know is quadratic in this density function, it actually doesn't change that, so it's invisible to that. It turns out that what's invisible to one marginal is quadratic in the other. So the combination always gives you constraint. Okay, so some nice pretty pictures. Now, let's look at some simple examples to finish off with, and then I will talk about some Bayesian work. Okay, so this is an example from the paper, a toy problem. We're trying to fit the blue to the orange. We have no model here. We've just simply got three parameters in the blue. We've got the amplitude, we've got the time shift, and we've got a frequency change. So this is a double Ricker wavelet, and by changing these three parameters, I can predict a new waveform blue, and I'm going to try and fit the noisy double Ricker and orange. Okay? There we go. So here are the misfit surfaces of the L2 norm at the bottom as a function of time shift and amplitude. And on the top right, we see the W2 Wasserstein, so that's using p equals 2, where you're using squared distance. And on the left, it's W1. And you can see that it's globally quadratic, even though it looks like there's no data there. You can see from the contours below that that's actually quadratic in both directions. And this one has got a crease, it's linear. You know, so it's classic L1 surface and L2 surface for this problem, even though we're changing amplitude and time. So with these ideas, we carry over that simplicity. We get a nice single global minimum misfit for this toy problem, whereas the least squares naturally has many folds, increases, and local minima. Now, full details are in the paper. So my final example is a bit more involved. It's using an earthquake. The Japanese earthquake making 6.6, the Fukuoka earthquake of 2005. This is a simulation, but it's using exactly the stations and the distances and the frequencies of the real data here. So on the right-hand side, I'm showing two stations of the 11 used here as a function of a source, which is, so we're moving the source around here. We're not changing the structure. The blue are seismograms from the true source to these two stations, the north, so the vertical, and the two horizontal components. The grey is, let's say, my starting model. They're the predicted seismograms from my starting model, which is a bit far away, my starting earthquake. I'm going to try and just locate the earthquake. Yeah? It's so far away that the cycles are skipped here. Yeah? So we are outside the linear regime. Yeah? So if you look at the grey, the main peaks are not necessarily in the same. You can certainly see it in the vertical here. They're not lined up. Yeah? So we are outside that linear regime. Simple linear methods would have trouble, as we'll see. And below, in the bottom panel of the two, I'm actually showing only the time density functions for the truth, which is coloured blue, and the grey, which corresponds to the grey curve above. So these are now our positive functions. We're going to fit these time, amplitude, density functions with optimal transport, with Wasserstein, rather than the waveforms with least squares. In fact, we're going to do both and compare. Okay? These are the details of the setup here. So I actually have 33 pairs, I have 33 seismograms I'm fitting at once here for a location of the source, and also with the moment tensor of the source. That becomes a 9-dimensional problem. That's less important because the moment tensor is a linear problem. It's the source which is the nonlinear. And we're using Andrew Valentine's, O'Toole, Valentine and Woodhouse's pi prop 8 code, which is essentially, the details are not so important for this example, but they are displacement seismograms, essentially high-rate GPS. Yeah. So we actually do have non-zero average times in this because we're calculating it with this forward code. Okay, so on the left-hand side is the misfit surface as a function of 4 slices with the least squares algorithm. Yeah? And on the right is the Wasserstein. So at depth here, the black dot is the true location, which is at 20 kilometers depth, and I've got slices at 40, 30, 20, and 10. And you can see at depth, there's very little problem. The least squares works very well. It only really sees a quadratic surface as a function deep. But as you go closer to the surface, many local minima occur because of the influence of the station and misalignment of phases. Yeah. And this becomes traps for a location algorithm. On the right-hand side, you see the Wasserstein distance here, where I've, in general, I would say a weighted sum of the time and the amplitude, and I've taken alpha equals 1, so I'm actually only using the time in this case. Yeah. And you can see that the surface is almost globally. It's not guaranteed to be globally quadratic, but I have a single global minima. So one would expect that this surface, and it's we're just seeing slices in 3D, would be easier to optimize than the one on the left. Yeah. For this problem, I could probably enumerate it. It's not an impossible problem. I'm just using it as a demonstration. Okay? So to back that up, what I've done is a whole series of tests there. The details are in the paper, using local optimization of both the Euclidean norm and the Wasserstein distance from different starting points, which are the blue dots here, across in lat long and also in depth. And we're going to try and repeat those optimizations from different starting points and see where we converge to. On the right-hand side, I've got the error in the OT solution versus the error in the L2 solution. So if you're inside the dashed line on either case, I'm considering it as converged. Yeah? And we can see that in extreme cases, both do not converge. Yeah? So both get trapped. But many also get trapped. The L2 gets trapped here, whereas the W2 doesn't. So it's just trying to back up that notion that we saw, that it actually materializes that when you do local optimizations, 41% converge to of the least squares norm and 77 in this case for the W2. So we've improved, okay? And this is not optimal. It's got tuning parameters. They're somewhat arbitrarily chosen. But it's a demonstration that you can do this. Okay, so I just want to finish off with an exploration beyond misfit functions into Bayesian inference. So, in Bayesian inference, that many of you will know, Bayes' rule connects a posterior distribution P of M, prior distribution P of M to a posterior distribution P of M given D. So this is a framework for all inference. And the standard methods of Bayesian inference are usually Markov chain Monte Carlo. Yeah. So this is our prior, this is our posterior, and what it actually does, it's a bit similar to least squares, of course. It's comparing, Bayes' rule compares essentially the amplitude of the posterior to the amplitude of the prior, connects the two at a given point in model space. Yeah. Whereas optimal transport for this problem, given by the transport equation here, compares the prior to the corresponding point on the posterior that the map would take us to. So one is fixing ourselves at a location, and the other one's saying, no, let's find the best place to move to. And this, I think, creates the potential, and I'm just going to suggest there's potential here, of using optimal transport in general for Bayesian inference. Here's a little test problem that Matthias, he's probably in the audience somewhere, will recognize as part of his PhD, a simple little toy problem to illustrate what I'm talking about. We have a sphere, let's call it the Earth. We have an inner sphere, let's call it the core. Given the mass of the Earth, or the mass of the sphere, the question is, what's the radius and the density of the inner core? It's an underdetermined problem. If my radius, outer radius is 1, and my outer density of the shell is 1, I can look at how the constraint I place with one observation, 2 unknowns, on the radius of the core and the density of the core. And there you go. It's a completely underdetermined problem. A classic little toy problem. Okay? So, the question is, can I illustrate the concepts of Bayesian inference being attacked by optimal transport with this problem? Well, here's the truth. It's a simple toy problem. On the left is the prior we're using for RC and V. It's Gaussians, in one direction, not in the other. The likelihood given by a simple least squares measure is here. So there's my prior, there's my likelihood. Multiply them together, there's the posterior. That's the problem solved. But you see there's a two-peaked posterior. So I'm going to apply optimal transport to this problem, or at least to illustrate what it could do for this problem, here. So I'm even going to reduce you down to one parameter. This is just the radius, okay? So in terms of the radius, here's the prior in green on the top left, there's the posterior in blue. If you solve for the transport problem here, you get a transport map in the top right, which maps every point on the prior to every point in the posterior. Yeah? We use that map if we draw, for example, samples from the prior and then propagate them through the map, we get the case in the bottom right-hand side. Okay? We've generated samples who's distributed according to the posterior. Yeah? And by definition, you will do that. That's part of the process. Any component of the prior, any moment you want of the posterior can be converted to a moment in the prior that we know, use the transport map and solve it exactly, if you can estimate the transport map. And you can see we do this without MCMC here. We're only using the prior. And here's the same thing for the density of the radius. It's the same type of result here. The prior, posterior, prior results. There's the top right-hand side is the Bayesian map. And if you apply, in this case, I'm just generating samples according to the prior. I push them through the map, and I get samples according to the posterior. So it's solving Bayesian inference without MCMC. Now, I haven't actually solved the problem here. I've just illustrated. To get the map here, I've taken the prior and the posterior. Okay? I haven't solved for the prior from the data and I haven't solved the map from the data and the prior. So I haven't really done it. I'm just illustrating what would happen if you could do it, i.e., every property of the posterior you want could be converted into a property of the prior, or even some intermediate distribution. This can work in stages. Yeah? And if you can estimate, so what I'm going to suggest is that converting, another way of looking at Bayesian inference is not to estimate the posterior, is to estimate the Bayesian map. And if you've got the Bayesian map, you've got everything. Okay, so here's the 2D example, just as a final slide to illustrate where we are. The posterior on the left, on the right-hand side is the posterior estimated by the transport map, which you can see is very similar, the colors that is. And the lines here are essentially part of the transport map, i.e. where it starts, and where it would move to the posterior. So you get this idea of this sort of fuzzy, hairy mess where points in the prior would be moved by the map to the posterior. And it makes sense that they're moved to the areas of high density on the posterior. Yeah? Okay, so I just want to conclude with 3 points. So in the paper that I pointed you to, we've proposed a new approach to optimal transport for time series, yeah? Particularly for time series, because the focus is on how do you make a positive density function out of an oscillating time series. And we've proposed a way we do that which we think makes sense and avoids some of the complications of previous methods. Our approach, and I think there's a lot to be said for, is to exploit analytical solutions. There's a lot of work in how you solve optimal transport in higher dimensions, and you can do that, computational costs. I think that's a challenge, that's an open issue. If you can exploit 1D solutions, you've got analytical results, but you've also got derivatives, which is important from a fitting perspective. If you're not fitting, then you don't really need derivatives, but you've got them analytically and exactly if you use the 1D case. But you can also generate them from higher dimensional problems as well with some of the other approaches. And I think Bayesian inference could be, I think it's a challenge, there's an open question, could be approached with, from a perspective of, let's call them Bayesian maps, transporting the prior to the posterior. This is by no means done, okay? All I'm simply saying is it's a potential way of going forward, and I think something interesting for the future. I'll leave it there. Thank you.
Thanks a lot, Malcolm. It's already coffee break time. You've been so enthusiastic, but I think we're going to take maybe 1 or 2 questions, if there's any. Yes, Gauthier.
Thank you very much. That was so interesting. To put it quickly, can you... I find it is interesting how you can make a model that is in between something and another model, so using that in your first examples. But can you add some constraints to that, like to say, for example, I want the topology of the model to remain roughly the same or avoid certain things you know are not possible in between. It's maybe different application, but can you add constraints?
That was a comment, not a question. Exactly.
The question, I guess, is can you add constraints to the optimization problem? Like you have a big wall where you don't want the points of the transport map to cross, for instance.
Yes, absolutely. That pushes you into an optimization framework, but it's already a constrained optimization problem, so you could add other constraints. There's not really a lot of work on that, as far as I know. Bruno might be able to say more, but in principle, yes, absolutely.
Yeah, Florian?
Thanks. Also, just a quick question. This Bayesian map example is really nice. I think this idea, it bears some similarity to these particle flow methods. Do you know of those, and if there is a similarity? The particle flow maps for Bayesian inference.
The question is there a relation with particle flow? Well, maybe, yeah.
So, of course, that last figure is suggestive of that. I think there probably is. I don't know of too many papers that deal with that, but essentially is a flow problem from the prior to the posterior. There are papers about the connection between optimal transport and fluid flow. So there are equivalents there, and the Monge-Ampere equation is one of those that connects the two. So yes, fluid flow problems and Bayesian maps are closely connected, absolutely. It's not something I know a lot about, though.
Okay, thanks a lot for the very exciting presentation.
Okay.